If you guys would, have your equation sheet out, and also go ahead and turn in your book to the chart on page 841. It's that standard reduction chart, the smaller one. So, if you guys would, on your equation sheet, flip over to the back side. There is a section that says thermochemistry / electrochemistry. Okay, and what we're going to do today, besides finishing this chapter, because it's a short chapter, is I'm going to show you how the concept of electrochemistry can be tied to other major concepts in AP Chem. For example, thermochemistry and electrochemistry very often go together. And this equation is kind of like a gateway to get you from electrochem to thermochemistry concepts. So let's just review. First and foremost, this equation, you don't have to memorize. It is on your equation sheet. If you will look, it is the second to last equation there in that electrochemistry section. All right, look back at your notes from last class. What is this called? Not in your physics class, but in here in chemistry. What do we call this? Cell potential. What are its units? Volts. It's a voltage. Okay. We used this, or we talked about this concept, and we calculated cell potentials for a galvanic cell. What's another more everyday term for a galvanic cell?
Battery.
A battery. Okay. I'll talk in a minute about what that lowercase n and f, I'll talk about that in a minute, but this we have seen before, although it's been a while. This is Gibbs free energy. Do you guys remember what is the one and only reason you would ever want to calculate delta G? To tell you what? Right. Is this reaction thermodynamically favored or not? Okay, let's see what you remember. If you do calculate delta G, and let's say delta G comes out to be a negative number, do you remember what that indicates to us? It is favored. Okay, great. Well, come back to cell potential. That's what we were doing last class, calculating. Do you guys remember from class on Monday that a galvanic cell always includes two half reactions? We have to flip one of them. Do you remember how we made the decision of which one to flip? So that our total added cell potential would be a positive number. Okay? As I said, I will talk about these two, but for the moment, guys, know that this number and this number are positive. If this is positive, this is positive, this is positive, there's a big negative sign here. This comes out to be negative. And what does a negative delta G mean again? Favored. Well, guys, we talked about this too. A positive cell potential means a galvanic cell that runs spontaneously, okay, on its own, without any outside intervention. So these things are connected to one another. Okay, now let me tell you what N and F are. Okay. Again, look back at your notes from Monday. When we set up these half reactions and we added them together, what was it that absolutely had to cancel out? The electrons. This lowercase n is the coefficient associated with those electrons that you canceled out. If when you added your two half reactions, you canceled out 3 electrons and 3 electrons, then you would plug the number 3 in that position. That capital F is something called Faraday's constant. You don't have to memorize it, ladies and gentlemen. Move your eyes over to the right. It is given to you right there. Okay? But guys, the take-home message here is I can now connect electrochemistry and favorability together with this equation. A positive cell potential means a galvanic cell that it runs on its own, favorably, spontaneously. That's also what a negative delta G means. At the end of class today, guys, we will see a situation where the cell potential is negative. Okay, we'll see that, which is something that is non-spontaneous. It is not favored, will not happen on its own. Okay. Can you all tell me, what does that little degree symbol mean? Standard state conditions. Well, let's review that. What is the temperature under standard state conditions? 25 degrees Celsius. Why the number 25? What's significant about that? Yeah, it's room temperature, okay? What is the pressure at standard state? 1 atmosphere. And what is the molarity of anything aqueous? 1 molar. Okay. Well, here's the thing, ladies and gentlemen. What if you have a nice, happy little galvanic cell under all standard state conditions, and you come along and you change something about the situation so that it is no longer at standard state conditions? You're not going to have to calculate anything, but you will have to predict what happens to the voltage of that galvanic cell. We're going to make some changes to these galvanic cells, and we are asked to predict, will I be getting a greater voltage because of this change, or will I be getting a decreased voltage? We're going to use this as our example, this electrochemical reaction, just so you kind of have your bearings. All right, all galvanic cells would have 2 compartments. One of these compartments would have a bar of aluminum. That electrode, that bar of aluminum, would be immersed in a solution that has aluminum ions. The other compartment would have a solid bar of, what's Mn? What element is that? Manganese, and it would be immersed in a solution with manganese ions. The electrodes are connected with a copper wire. What am I drawing here? What's this called? A salt bridge. Okay, so this is the galvanic cell setup for this electrochemical reaction. Now look at what I'm going to do here. Remember, all things aqueous are, in standard state conditions, 1 molarity. Okay, great. Well, I haven't changed this one at all. I have completely left the manganese side of this galvanic cell. I've left it alone. But I've changed something about that aluminum solution. And you guys tell me, normally it's 1 molar. Have I added more aluminum ion or taken some away? I've added more. It's greater than it was before. So, okay, aluminum ion. Where is aluminum ion? Here it is. Think Le Chatelier. I have increased the amount of aluminum ion in this reaction. Will I get a shift? Yes or no?
Yes.
Which direction? To the left. Okay, great. Well, guys, we read chemical reactions just like we read and write in English. We look at them from left to right. Now, go with your gut instinct here. this galvanic cell is supposed to run with the reaction going from left to right. I have just done something to cause a shift in the direction that I don't want to go in. Go with your gut instincts. Do you think making this change, is that going to give me more volts coming out or less volts? What do you think? You're right, less. So this is what I would write. I would write E cell, please notice, I did not draw the little degree symbol. Pushing this system out of standard state conditions. All I did was change the molarity of one of them, but that makes the entire cell no longer at standard state conditions. My new cell potential is less than what it was before. I have made this battery less efficient. Now, why would you do that? I don't know, but you may have to make these predictions. Okay, let's look at another situation. How about this? This time, I'm leaving the aluminum solution alone. I'm leaving it at 1 molar. But now I'm going to add more manganese ion. Well, where is the manganese ion? Here it is. Will that cause a shift if I add more? Yes or no? Okay, which direction? To the right. This time, this change that I have made has caused this reaction to go in the forward direction even more than it was before. What do you think? Am I going to be getting more volts? You got it. This is like putting a battery on steroids. Okay. Right. I'll be getting a little bit more voltage than I was before. Right? I've just souped it up a little bit. All right. Let's do a few more situations. Go with your gut instinct. What do you think? No effect. Okay. The potential would stay the same. What if I did this? What if I changed the molarity of the aluminum ion to that? What have I done? Have I added more, taken some away? What is the molarity of these ions usually? 1 molar. Well, now it's less. Where is aluminum ion? There it is. It's as if I took some away. What do you think is going to happen here? It's going to shift. What kind of volt? What's that going to do to the cell potential? It's going to increase it. Okay. Let me give you one final scenario. What if, look over here, what if I increase the size of that manganese electrode? Like I just make it bigger. What would that do? I haven't changed anything about the solution. I have increased the mass, the size of the solid manganese electrode. What's going to happen? What do you think? Why nothing? You're right.
Because it's still gonna make flow.
It has to do with its state of matter.
No, because it's a solid.
Solids have no effect on equilibrium. Okay? I can make this manganese electrode very, very small, very, very large. Doesn't do anything. As long as there is some solid manganese there to have an electrode, I'm good to go. How big it is doesn't matter. Okay? You're not going to have to calculate these new cell potentials, but you will have to predict whether it will be less or greater than it was before. Okay? All right. Don't write this down. Don't write it down. These are equations that if you had to calculate a non-standard cell potential, you would use. It's called the Nernst Equation. I only show it to you because those of you that will go on to chemistry in college, you will use those. Okay? But that's not on the AP exam anymore. You don't have to calculate that cell potential. You just have to predict, is it greater or less than? Right? This, however, you do need to know. All right? It says, at equilibrium, notice this says E cell non-standard. Okay, there's no degree symbol there. E cell non-standard equals 0. Guys, how do you describe a battery that is giving you 0 volts? Dead battery. Guess what? When a battery has gone dead, all that means is this galvanic cell has reached equilibrium. That's all that means. A working battery that is putting out volts is nothing more than a galvanic cell trying to get to equilibrium. If you are in some parking lot with a dead battery because you accidentally left your headlights on for hours and hours, let the silver lining of the situation be that your battery is in its happy place. Okay? There's always a silver lining in every situation, guys. Okay? So, you don't need to write these down. Okay, this is just another tweaking of the Nernst equation. Okay, just showing it to you. But let's talk about what do you do when, let's say, the battery on your phone has gone down. You have 0%. So what do? You charge it. Okay. Well, what does that even mean to charge a dead battery? Your battery that's dead is at equilibrium, right? Okay. So you plug it in. Well, what's flowing through the wire connected to your phone? Electricity, which is electrons. When you recharge a dead battery, all you're doing is pushing that galvanic cell out of equilibrium. How? By flooding it with a huge amount of electrons. Okay? So think about Le Chatelier's principle. You mess up an equilibrium system. You do something by adding a bunch more on one side. What happens? It shifts, right? Well, guys, when a galvanic cell, when an electrochemical reaction shifts, all that means is that is your battery trying to get back to equilibrium, but a battery trying to get back to equilibrium is a battery that's working. Does that make sense? Okay. It's kind of a weird concept to think of. That your battery, when your battery's in its happy place, you are not in your happy place. But that's what it is. Okay? Okay. So, you have your books open, right? You've got that reduction chart in front of you. Okay? Here's what I would like for you to do. I'm not going to walk you through this. You're going to do this problem on your own. You have 2 half reactions. You can look up their potentials in this chart. And I want you to calculate the cell potential. What's in letter A is everything we did last class. However, this is new. Pick up your equation sheet, guys. Do we have a way to calculate delta G if we know cell potential. Do we have an equation for that? Yes, we do. Okay. Now, look at that equation and move your eyes one equation up on your equation sheet. If you know this, do we have a way to find that? Okay. Now, we haven't used that equation in a very long time. So I just want to review some things with you here. That's our equilibrium constant. Okay. Gibbs free energy, guys, is in units of joules. What's T? Temperature, what unit must it be in? Kelvin. Okay, let's see what you remember. What's this? Not a rate constant. It's called the ideal gas constant, even though we're not really working with gases here. Do you have to memorize this? No, it's on the same side of your equation sheet, guys. Look at it. Look at your options for R. Does it matter which one I use?
Yes.
Which one do I have to use? Why 8.314? Because that's the only one that has units of joules. Okay? You guys take it from here. Start here. This is what we did last class. Okay, check your answers, guys. So, guys, just a couple of things to point out. When I solved for delta G, did I have to express my answer in kilojoules? No, I just did. Okay? But when you come back to this equation here, I absolutely had to have it in joules because this gas constant has units of joules in it. And remember to, I'm probably using the wrong word, but invert a natural log or get rid of a natural log. It's just e to the power of everything else on the other side of the equal sign. In your calculator, second ln. Okay? Now, let me just tie some things together for you. Okay? What does it mean? Tell me one more time. What does it mean for a cell potential, a galvanic cell, to be positive? What does that mean? This is a reaction that will happen spontaneously, favorably. Isn't that also what a negative delta G means?
Yes.
Okay. Well, look here as well. This is an equilibrium constant. Would you guys say that that is a large number, small number? Pretty large. Well, think about it. Equilibrium constants are always what divided by what? Products over reactants. Now, that's a huge number. Lot of product or a little?
A lot.
A lot. Like, a lot. Over a little reactant. Okay? Well, think about what that means. That means a reaction that is moving in the forward direction like crazy. Okay? Think about it, guys. These things all point to the same thing, a very favorable, spontaneous reaction. All right? We can bring all kinds of concepts together. That's why I love the end of the year when you can talk about not just one isolated topic, but multiple topics. And I'm going to show you a little graphic that, again, links some concepts together. Okay? You have this equation on your equation sheet. You have this one. This is that Nernst equation, which you don't have, but you don't need it. If you have any one of these pieces of information, you can find the other two. And are you ready for this? I'm just going to give you a little foreshadowing of what you could see on a final exam or an AP exam kind of situation. I can link in a electrochemistry situation, like a galvanic cell, together with thermochemistry topics, entropy, enthalpy, which I could link to equilibrium, and equilibrium might have an ice table in it. Oh, this is good. Yes. All right. I mean, we could we could bring in all kinds of stuff. I mean, I'm excited. I know, I'm sure you are too. Okay. Now, am I going to do this to you on our electrochem test? Probably not, but final exam and the AP exam, you should expect these things to be tied together because they can be tied together. Okay? Smile, everybody. All right. Let's talk a little real-world connection here. Guys, if you would, go back and look at the problem we just solved. What was our cell potential value for E cell? What was it? 0.32 volts. Can you power a car on 0.32 volts? No, this should be a resounding no. No, you can't. Okay? Well, if you look at this chart, even if you took, had the best combination of the two half reactions, at most you can get like 3.5 volts out of a galvanic cell. You can't power a car on 3.5 volts either. So how do we have batteries that can power a car? Many galvanic cells. We talked about this a little bit. Okay? More than one galvanic cell connected in series. Okay? You don't need to write this down, but I just wanted you guys to be aware of the electrochemical reaction that takes place in a car battery. Car batteries are called lead storage batteries. Okay? I want you to look at this reaction. Why is it terrible, and maybe even against the law, I don't know, to throw away a car battery? Why would that be a terrible thing to do? Where does garbage end up? Landfill? Okay. What's any red flags jumping out here of things you probably don't want in a landfill, which ends up in the groundwater, which ends up in our running water? Lead. It's poison. Causes brain damage, people. Okay? This is why you don't throw car batteries away, or really any batteries. You take them to one of these battery recycling places. I don't know what they do to them, but magic. I don't know. Look what else is in a car battery. Sulfuric acid. And it's not just sulfuric acid. It's sulfuric acid at a very high concentration. If you are ever jump starting a car, hopefully you're not, but chances are someday you're going to have to do that because you'll have a dead battery. If any of you ever see this like white crusty stuff around one of the electrodes of your car battery, just be careful. That's going to be acidic. It can burn you. Okay? So please do not go hacking into your batteries because that's just a bad idea. Okay, now, ladies and gentlemen, the concept of corrosion is an electrochemical issue. Okay, now, what does that word even mean? The spontaneous oxidation of a metal. And I want to clear up a pet peeve of mine, and I have a lot of pet peeves, so if anyone's keeping track, write this one down. Okay? Instead of saying that this particular metal or whatever it is corroded, a lot of people will use another verb. This thing didn't just corrode, it rusted. Okay? Ladies and gentlemen, rust is a form of corrosion, but it's for a very specific metal? What metal?
Iron.
Iron. Okay? You don't say, my aluminum bicycle rusted. No, you don't say that. That's wrong, and that bugs me. Don't be ignorant. Okay? You would say that your aluminum bicycle corroded. All right? Only iron can rust. Okay? Now, here's the thing. All right? Structural metals. Okay, what would you guys say is the number one component of building materials? Like, what are most buildings? They're skeletons. What are they made of? Steel. What's the number one element in steel? Iron. Okay? Guys, iron, when exposed to oxygen, spontaneously will corrode. Well, that's a real problem, because if all buildings are made of iron, then your building is corroded, then your building collapses and people die, and that's a real problem. Okay? So, let's talk this out. I want you, please, to look at this reduction table in your book. Find this half reaction. It's just slightly below halfway. Find it, put your finger on it. Now let's do something that we did last class. Will oxygen and iron metal, solid iron, will they react spontaneously? Find iron solid in the chart. Find it. Is iron solid on the reactant side? Yes or no?
Yeah.
No.
Wait, no.
And it needs to be. In order for two things to react, they both need to be reactants. How do you fix that problem? Okay, we're going to flip that iron equation. Now you guys tell me. This half reaction put together with the iron half reaction flipped, do I get a positive total?
Yeah.
Yes. I do. Okay. Positive total, that means yes, iron will spontaneously corrode when it's exposed to the air. What other metals will also corrode if exposed to the air? Zinc. What else? Aluminum. Nickel. Guess what? Here's that oxygen equation. Any of the metals below it will spontaneously corrode. What would be a metal that does not spontaneously corrode when exposed to oxygen? Silver. Silver is above it. Well, if silver, when combined with that half reaction, gives us a negative total, which tells me that's a reaction that won't happen, that's great. Silver doesn't corrode, so why don't we build all of our buildings out of silver? Too expensive. And if any of you know things about metals, silver is a soft metal, okay? It's more malleable than steel, okay? That would be a bad choice for building material, because then our buildings would be like, okay? Gold is another metal that doesn't corrode. Platinum is another one. Now, platinum is very strong, but what's the problem? It's too expensive, okay? So, iron is what most buildings are made of, but there's a problem with that because iron corrodes. If any of you are thinking about going down the engineering path, the prevention of corrosion is a billion-dollar industry. Okay? So I want to show you what the process of corrosion really is. Corrosion is actually a little mini galvanic cell. Okay? Let's imagine that zinc is the metal that is corroding. Here is the anode, the reaction that we flipped, right? Okay. the electrons flow from anode to cathode. That oxygen reaction is like my cathode. Okay? Water speeds up this process. Salt also speeds it up. Okay, so let's do a little like pretend experiment here. Let's say you and your best friend lives in Virginia Beach. Okay? You live here, your best friend lives in Virginia Beach. You both have the same identical bike. And both of your bikes are made of steel, which is really being made of iron. Okay? You both take your bicycles and you leave them outside for 2 months. And let's just pretend that we have exactly identical weather conditions. Now that's unlikely, but let's just pretend. Anytime you're in some sort of seaside beach community, that entire environment is going to have more salt. There's more salt in the drinking water in beach areas. There's more salt in the air. There's just saltiness everywhere. Okay? Your friend's bike in Virginia Beach will rust over before yours does. Okay? Because salt increases conductivity. It makes the electrons able to travel faster. Okay? Yours will rust over as well, but your friend's bike in Virginia Beach is going to corrode over a lot faster than yours. What is it, guys, in the wintertime? What do they put down on the roads when it gets icy? Salt. Okay? And then you drive over those salty roads. What is your car made of? The skeleton of your car is made of steel. Okay? So when you drive through a wet, salty street, you are spraying the perfect material to cause your car to start to rust over. Have you ever seen cars in like a junkyard and they're all rusted over? Well, how come our cars don't rust over in the winter? I mean, are the cars that we're driving, are we driving in these bare steel boxes? No, hopefully not. What's keeping the water and the salt away from the steel skeleton of my car? Paint. Okay? Cars are not just painted to make them look nice, they're also painted so that you're not driving a rust box. Okay? Anything to keep out the water and that salt is a good idea, but God forbid you ever get into some kind of an accident, even just a fender bender. If the paint job on your car gets chipped and the steel of your car structure is exposed, get it fixed ASAP. Because guys, once the rusting corrosion process starts to take hold, it's like a virus. Okay? It spreads and it's hard to stop it. Okay? So if you ever get a chip in your paint job of your car, get it fixed because you don't want the structure of your car to be compromised. Okay? So, let's talk about what we do to prevent this. Chemical engineers, this is a huge business for them. Okay? Anything to keep out air, anything to keep out the water. Okay? Sometimes you'll see a process called galvanizing. Okay? Galvanizing means zinc is somehow involved, okay? A lot of paints have zinc metal in the paint. Now, what's so special about zinc? Well, look at your chart here, right? Find for me, please, one more time, that oxygen half reactions. Put your finger next to it. Okay, move your eyes down. Zinc metal and iron metal, their half reactions are right next to each other. You tell me, which combination, oxygen with iron or oxygen with zinc, which one is going to give us the more positive cell potential? The zinc. Well, guys, the more positive the cell potential, the more favorable that is. If you have a piece of iron and zinc right next to each other, exposed to the same oxygen, the zinc will corrode before the iron does, because this is a more favorable reaction. Okay? So sometimes they will put zinc in the paint of, like, well, here's another great industry. Not just building buildings is this an issue. How about the shipping community? What is, let's say, in the military, Navy, let's say an aircraft carrier. What's an aircraft carrier made of? Steel. What is it floating in?
Salty.
Salty water. Well, that sounds like an awesome combination for the entire aircraft carrier to completely rust over. So what do? They paint it all the time. I don't know what the lowest of the low rank in the Navy is, but whoever that person is, they'll dangle this person over the side of the boat, and that person all day will just paint the side of the boat. All day. And they move their way all the way down the boat. You know what that person does when they get to the end of the boat? They go back to the beginning and they keep painting. Okay? Fun job. All right? But it's better for the zinc in the paint to corrode before the entire hull of your billion-dollar aircraft carrier does. Okay? Sometimes they will do something called cathodic protection, which sounds very crude, but sometimes boats will, instead of putting like zinc in the paint or something, they will literally attach a strip of magnesium or a strip of zinc right around the water line of the boat, because that strip of metal will corrode before the hull of the ship does. Okay? And I love this term. Something like that magnesium, or if they put a zinc strip on the side of a boat, they call it the sacrificial metal. Because it sacrifices itself so that the hull of the boat can be maintained and not corrode. Okay? And if any of you are thinking, well, okay, let's say they do put a strip of magnesium all around this boat and that corrodes, aren't they going to just have to replace it? Yes. But magnesium and zinc are cheaper to replace than an entire hull of a boat. Okay? So this is big business, preventing corrosion. Okay? Okay, this is our final topic, ladies and gentlemen. You have a galvanic cell, which is what we've been talking about mostly. There is also something called an electrolytic cell, which is running a galvanic cell backwards. Okay? That means moving the electrons in the opposite direction through the wire. Do you think that's going to happen on its own? No. Okay? An electrolytic cell does not run spontaneously. Those electrons do not want to move in that direction, so you have to force them through the wire, because this is a non-spontaneous process. Electrolytic cells, guys, have negative cell potentials. Okay? Non-spontaneous. Do you all remember from last class, maybe you do, maybe you don't, that when you run a galvanic cell, one of your metal electrodes is gaining mass over time and the other is losing mass over time? Well, what if you want the other electrode to be the one gaining mass? Then you have to run your cell backwards. Okay. So we're going to play a little game here. How many of you guys like these puzzles where you have like two pictures side by side and you have to find the differences between them? I love those. Okay? We're going to play a little game here. I'm going to flip back and forth between this slide and the next. This is a galvanic cell. What's on the next slide is an electrolytic cell. There are 3 big differences. One of them will be immediately very obvious. Are you ready? Are you ready to play? All right, here we go. This is fun, isn't it? I'm having a great time. Okay, yes, besides the fact that the electrolytic cell is slightly larger, okay, that was just my formatting mistake, all right? Okay, before we point out the differences, what is this turquoise box supposed to represent in this galvanic cell? A voltmeter, okay? It's measuring voltage. Okay, so what's the first most obvious big difference? Yeah, this isn't a voltmeter. It's a battery or some kind of power source. Okay, remember what we said. Electrolytic cells run in the direction that that is not favorable. It has to be forced. You need a power source. Okay, what's one other difference? Okay, cathode, anode. Even before we get to that, how about the direction of the arrow? Okay, the electrons are flowing in the opposite direction now. But guys, this brings out the third difference, anode versus cathode. Do you remember what I said last class? Electrons always flow from anode to cathode, no matter what, even in an electrolytic cell. Now, just to be clear, did zinc and copper, did they flip sides? No. But the location of anode and cathode did. Okay? Now, there is math associated with this. It's easy. I'm going to walk you through a sample problem here. Okay, and those of you that are gifted in physics, you're going to help me out here. This says, we're going to do letter A together. What mass of each of the following substances can be produced? For example, in letter A, I am trying to produce solid cobalt. Okay? How much can be produced in 1 hour with a current of 15 A? What's A? Amps. Okay. Those of you that are gifted in physics, what's another way to write the unit of an amp or an ampere? It's something per something. Coulombs per second is correct. What's a coulomb? Yeah, it's a unit of charge. Okay. Let me ask you another question, and please think before you answer, because I got some interesting answers this morning. Think before you speak. How many seconds are in 1 hour? Think before you speak. Thank you. Thank you for not saying 60, because that's what everyone does. How many seconds are in an hour? 60! No, there aren't. Okay. 3,600. Okay, seconds cancel. And we do the math, we get 54,000 coulombs. Okay. If you guys would, pick up your equation sheet. Look at where Faraday's constant is. What are its units? Coulombs per?
Mole of electron.
Coulombs per mole of electron. Watch. Learn. coulombs per 1 mole of electrons. Now guys, I want you to understand what that number is I just found. This does not matter for any of these. This will be the same for all 3 parts. If I run an electrolytic cell for 1 hour with a current of 15 amps, that means I will be able to force 0.56 moles of electrons through the wire. That's what that number is. How many electrons can I force through the wire? Now let's come down to letter A. I am trying to produce cobalt. And what's my starting material? Cobalt ion. Please tell me what's going to fill in the blank here of this half reaction? 2 electrons. Okay. I'm ready to do my calculation here. Watch what I do. I'm going to take those moles of electrons. Two moles of electrons will be moved through the wire for every 1 mole of cobalt solid that I produce. Can you all see now how I'm going to get to grams of cobalt? Yes? No? Maybe so? Okay, you're closest. What's the molar mass of cobalt? 58.9, he says. Comes out to about 16 grams of cobalt. That means if I started with a cobalt electrode immersed in a solution of cobalt ion, I run this electrolytic cell for 1 hour for 15 amps, I can gain 16 more grams of cobalt. Now, for B and C, which you're on your own for, nothing up here is any different. The only thing that'll be different will be this number and the molar mass. Let me just give you a head start on letter C, because this one looks a little different. What is the charge of chromium within this compound right here? +6. You take it from here. Go. All right, check your answers. That's it. Okay, that's the end of the chapter. It's the last material before the AP exam.